Hi, and welcome to the class on the practice and pitfalls of studying organic reaction mechanisms. I'm Marc. I'm here in my office at the University of Strathclyde, and I will be taking you through the lecture content and assignment over the next month. In this class, I didn't want it to be a comprehensive textbook, know-all exercise on mechanisms. There's lots out there that you can read and digest in your own time. Instead, what I wanted to do was revisit some of the basics, indeed some of the things that you will likely have come across in your undergraduate studies, if not during your PhD. And what I want to do in that approach is to go over some of the things that I have found to be difficult, that I have found to be causes of simple mistakes. And by the end of the class and through the assignment, what I hope you can take away are alarm bells for some of those easy mistakes that can pop up in studying mechanisms, so that you can avoid those and teach other people to avoid those in your career going forward. So what will we actually look at? So the course will be divided down into 5 lectures, which I'll record like I am now. I'll record with PowerPoint slides that you can watch, study and digest in your own time. In the first lectures, we will look at things like order of reaction, molecularity, and elementary steps. What do these terms mean? And we'll build on that to look at things like equilibrium. What does steady state mean? What does pre-equilibrium conditions mean? Terms like that. And we'll build on those with examples. We'll then go on to look at how temperature affects reactions and reaction rates. What happens when we start to study reaction rate alongside temperature, and what can that tell us about reaction mechanisms? Moving on from there, we'll start to look at other types of relationship, most notably the Hammett relationship, and how that can give us complementary information about reaction mechanisms. And finally, we'll tie this all up by looking at the difference between linear reactions, things that go from A to B or A to B to C, to catalytic reactions, which are of course in a cycle, and how that affects how we can study reaction mechanisms and what we need to do to understand that. The assignment I'm trying to make as flexible as possible. Again, you can do that in your own time, having digested the lecture content. But I would like you to do one thing right now for the assignment, and that is to pick a paper that you've liked over the past 5 years, one paper, no more than that, and make it a paper in the realms of organic methodology, organometallic chemistry or catalysis, something to do with reaction development. The one stipulation is that it has to be a paper that is not so much about a mechanistic understanding, but more about the methodology development. And in your assignment, what you will be tasked to do is to write a 1 or 2 page report, maximum, regarding what you would do to study the mechanism or mechanisms present in that initial paper. Another way to think about that is, let's say you released your first rapid communication on a new method, but then wanted to have a follow-up paper that looked into mechanism in more detail. Your assignment will be to plan what that second paper would look like. What would you want to study? How would you approach studying the reaction mechanism? And what tool or tools from the lectures would you use? And ultimately, from each mechanistic tool that you use, what information would you hope to gain from that in order to get you closer to a representative reaction mechanism or mechanisms based on the reaction from the paper that you've chosen? Finally, I'd like to say that as well as the 5 main lectures, you're about to watch now an introductory lecture, my more philosophical take on what it means to study reaction mechanisms, not just in chemistry, but in science in general. So without further ado, I really hope you enjoy the class and are able to take something away from it to study mechanisms in your own science. And if at any point along the way you have any questions or problems with the content, please feel free to reach out to me by email or through the class platform, and I'll contact you in more detail on the platform after this video. Thank you very much. Hi, and welcome to this introductory lecture on the practice and pitfalls of studying organic reaction mechanisms. For a class on what the title suggests, you'd be forgiven for thinking the watch was a strange addition to the top of the title slide. The reason I show this is to share the point that studying mechanisms is not chemistry specific. For whatever we are studying, understanding mechanisms is all about lifting the lid on a black box and looking inside. In the case of the watch, when we open it up and look inside, we can see the interconnected cogs and wheels that need to turn to make the watch tick. In chemistry, we don't necessarily care about this watch, but rather on how we can take real-life data of recording a reaction like this and use time course plots like these in order to understand the reactions that we design and study and hypothesize. We want to lift the lid on these reactions and understand what makes them tick. To take this general concept on studying mechanisms further, consider this short message from one of my scientific heroes, Nobel Prize-winning physicist, Professor Richard Feynman.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Now, this rather humorous video does of course contain an important message for studying mechanisms of any description. If your mechanism or guess disagrees with experiment, it is quite simply wrong. It doesn't make a difference if you're an undergrad, a postgrad, a postdoc or a professor. If your idea disagrees with experiment, it is quite simply wrong. We can look at Feynman's message in a flowchart like this one. When we start here at our guess, we can compute the predicted outcome of that guess and see if it agrees with experiment. If no, then it is wrong and we have to come up with a new idea and start with a new guess. If yes, then we can go to the next experiment and go round and round until we're happy that we have a mechanism or mechanisms consistent with all available evidence. Remember, a new experiment could always come along and disprove your guess, so we avoid ever saying that our evidence is fully proving a mechanism. We're always saying that the evidence is consistent with a mechanism. The final general concept I want to share with you relates to these other thoughts, and it's on this concept of trained incapacity. From sociology, trained incapacity refers to that state of affairs in which one's abilities function as inadequacies or blind spots. In other words, don't ever be too sure of your expertise. It's possible to be an expert in something and to point out that your expertise allow you to reject evidence in favour of a more established idea that fits with your expertise or knowledge or experience. Your expertise can act like rose-tinted glasses, distorting how you see things. Remember, if your guess disagrees with the experiment, it is wrong. Now, looking to the lectures, here's what we're going to be looking at. We've just completed the introductory lecture on what it means to study a mechanism, and the remaining 5 lectures look like what you can see here on the slide. So lecture 1, we will look at order and rates and steady state and pre-equilibrium and all these fundamental terms related with studying mechanisms. In lecture 2, we'll then look at how we can use isotope chemistry and isotopic labels in mechanistic studies. We'll then look at temperature effects in Lecture 3, linear free energy relationships like the Hammett relationship in Lecture 4, and then we'll finish in Lecture 5 with some thoughts on catalytic reactions. Now, all these lectures will be available by next week on Monday the 3rd of September. And finally, in relation to the lectures, of course, we have the assignment as shown here on this slide. Now, as I said from the introductory video before this lecture, I want you to pick one paper. Make it a paper on organic methodologies, organometallics or catalysis, something that is about the design and implementation of a new chemical reaction. Now, the paper has to be primarily a non-mechanistic paper, so preferably a short communication, a rapid communication that gets the new science out there into the chemical literature. And what you will be doing is to plan the follow-up paper that will investigate the mechanisms of the new reaction. So in other words, your assignment will be to create a 2-page report, no more than 2 pages, so a nice Word file with ChemDraw schemes and any diagrams that you want to use to describe what your plan is. And in that report, show your plan on the mechanistic experiments or tools you would use to study the mechanism. What would you expect to learn from each mechanistic tool or experiment that you've planned? And for that 2-page report, and giving you time to digest all the video lectures in your own time, please submit the 2-page report by the end of the month on the 28th of September. As before, for the lectures and for the assignment, if you've got any questions or issues, please feel free to contact me. So without further ado, I really hope that you've enjoyed this introductory lecture on the thoughts of studying mechanisms in more detail. It's time for us now to get on with the chemistry lecture content, and I'll see you back here for the remaining 5 lectures. Thanks very much for watching.